Jai Hind, welcome to class of Analog and Digital Communication. Today we are going to start with Unit 2, which is angle modulation. So these are the contents which we are going to cover today. We are going to talk about the basics of angle modulation, frequency modulation, phase modulation, generation of frequency modulation, FM receivers and demodulators. These are contents of the complete unit. What is angle modulation? So first of all, modulation is the process of altering the characteristic of a high frequency carrier wave with respect to instantaneous value of the message signal. That is what modulation is, altering a carrier with respect to the message signal. We know the need of modulation, which we have clearly discussed in our unit 1, that what are the needs of modulation. That we need to communicate to long distance, we need to reduce the height of antenna. With a shorter antenna, we want to communicate to longer distances. There is ease in multiplexing, there is ease in noise removal. So modulation serves us in many purposes. Now the question is, how do we do modulation, right? So if I take a general naturally available signal, like if I talk about a pure cos wave or pure sine wave, I may represent my pure cos wave by, right? So if I talk about a wave, it has these two properties. One, the amplitude of the wave, another, the angle of the wave, right? So when I talk about altering the characteristic of a wave, I would be either altering the amplitude of the wave, or I'll be altering the amplitude of my carrier wave, right? These are the only two ways of altering my wave. So when I alter the amplitude of my carrier wave with respect to instantaneous value of my message signal, that kind of modulation is called as amplitude modulation. And if I alter the angle of my carrier wave with respect to instantaneous value of my message signal, that kind of modulation is called as angle modulation. Now we have to look here clearly that what is an angle of a wave. Here I represent the angle with omega t, right? So this is a pure cos wave. Likewise, if I talk about a sine wave, a pure sinusoid, I'll be representing it with xt equals to a sine omega t, right? Which clearly starts from 0. Now, when this is the angle, or we may call it as phase angle. If it deviates from its natural angle, that is 0, then that will be called as phase deviation. So this is my phase angle, and if there is little deviation in it, that would be represented by right. So this deviation would be represented by plus minus of phi t. So this complete is the phase angle, and this much portion is the phase deviation, right? So angle or deviation in the complete angle. If I expand my this part omega, my omega is 2 pi f, and we have a part t. So this can be done by either varying the phase angle, or I can vary the frequency. When I vary the frequency, then also the complete angle of my wave gets altered. So I have two ways of varying my complete angle. Either I show some deviation in the phase, or by including some variation in the frequency, I can vary the complete angle of the wave, right? So when I talk about analog communication or analog modulation, I can classify my analog modulation in amplitude modulation, frequency modulation, and phase modulation. When I alter the frequency of my carrier wave with respect to instantaneous value of my message signal, that kind of modulation is called as frequency modulation. And when I alter the phase of my carrier wave with respect to instantaneous value of my message signal, that kind of modulation is called as phase modulation, right? So if I classify First of all, if I classify communication on the basis of what kind of message signal I have, if I classify my communication or modulation on the basis of type of message signal, I have either analog modulation, or I have digital modulation, right? In analog modulation, I have again amplitude modulation, frequency modulation, and phase modulation, right? Where my FM and PM, that is frequency and phase modulation, are combiningly called as angle modulation. These two are related. I cannot just simply vary the frequency without varying the complete phase of my angle, right? So frequency and phase modulation are related to each other. They comes under angle modulation. If I talk about digital modulation, I have techniques like ASK, FSK, we have amplitude shift keying, frequency shift keying, and phase shift keying, right? So this is the classification for my communication system. When the classification is on the basis of my message signal, that whether my message signal is analog in nature, that is a continuous in time signal, or a digital signal, that is which is represented by binary bits, right? And this part, amplitude modulation, we have covered in unit 1. So in unit 2, we are talking about angle modulation, which clearly has frequency and phase modulation. And if I want to represent it, then I have to take example of a signal. I have taken example of a signal which is a pure cos wave or pure sine wave, and I have shown which part is the complete angle of my signal, and how do I vary the angle, and how does angle variation is related to my frequency and phase, right? This is what I am trying to explain here. So I hope this makes sense. So when I'm talking about varying the angle part, it is done in two ways, either varying the complete, either deviating the phase or varying the frequency part, and both combiningly are called as angle modulation. In the previous slide, I have defined omega is defined as 2 pi f, and if I am talking it in terms of carrier, I would rather represent it with CT. I would represent omega with omega CT, and I represent frequency with FC, right? So varying this part would serve, or varying the angle completely would also serve, right? So we are going to talk about frequency modulation and phase modulation in detail in this unit, right? So when I say if there is a change in carrier frequency, or if I want to focus on frequency modulation for now. So let's talk about frequency modulation for a while and then we'll move on to phase modulation. If I talk about frequency modulation, then how do I depict the expression and how it is represented in waveform, right? If I talk about the waveform, we know an analog signal is represented like this. On x-axis I have time, on y-axis I have voltage or amplitude of the wave. A high frequency carrier would be represented like this. Here I can see that more number of cycles are here as compared to my message signal. Although if I talk about the practical communication, then my message signal is usually my audio signal, video or text, which lies in the range of hertz and kilohertz, whereas my carrier, which is in radio frequency range, that is in megahertz or gigahertz range. So this is quite impossible for me to show 10 to the power 6 time frequency here on this screen, but these two waves clearly shows that this is a low frequency wave and this is a high frequency wave. When I talk about specifically about frequency modulation, then the frequency of this carrier will be altered with respect to the instantaneous value of my message signal. And always I take my message signal as the voltage signal, which means as per the voltage or amplitude of my message signal, the frequency of my carrier will vary. So how does it vary? When the voltage of my message signal is increasing, the frequency will increase, and when it is at its lowest value, the frequency will decrease. So if I want to draw the resultant waveform here, I'll take some plots. I'll mark these things, that when the amplitude is highest, this frequency will become maximum. That means there will be more number of cycles per second, right? So if I want to draw it, although this variation would be analog in nature, that is there will be no abrupt change, there will be continuous change. So this frequency will gradually start increasing and it will reach the maximum value, and when the voltage decreases, it will decrease, and at this point of time it will have minimum frequency. Then again it will slightly start increasing. So this is how my frequency modulated wave would probably look like. There could be a better, neat diagram for it. So I believe somehow it makes sense that this is my message signal, which I represent by MT. This is my carrier wave, which I represent by CT, and this is my modulated waveform, which I represent by ST. Right? So if I want to check what is the instantaneous value of my frequency, so this instantaneous value would be somehow some plus minus some change, which I may represent by XYZ, maybe Y, right? So let's see how we proceed. Now considering the carrier wave, which could be CT, or you may represent it like VCT. I have VC, either instead of V you may write it AC as well, cos omega CT, plus here phi C represent the deviation in the phase. Here this complete term represents the angle of the carrier, which is true as we have discussed. Now there are two ways of varying the angle of carrier, by varying the frequency as discussed before, or by varying the phase, right? Now let's talk specifically about frequency modulation. The waveform I have shown. Now let's see how I may represent the expression of an angle modulated or frequency modulated waveform. In FM, the message signal MT controls the frequency of the carrier. Now consider the carrier Vc equals to Vc cos 2 pi cos 2 pi FCT. That is, I am considering my carrier wave to be a cos wave. Now what will happen? For FM signal, there will be some frequency variation, right? If I expand my omega c, this is my 2 pi fct. Now I have to change this part specifically. So Vc cos 2 pi fc plus some frequency deviation. That is what I have to consider, where the frequency deviation will depend on mt, which is my message signal. True. Now given that the carrier frequency will change, we may write for an instantaneous carrier signal. If at a particular instant of time I want to see what is the value of my carrier signal, when I want to represent it in terms of expressions, I'll be representing it, I'll replace omega c by omega I, that is the instantaneous value of my angle. And what will be that? Here there is a variation in frequency, so I'll talk about specifically the instantaneous frequency. So because of the change in frequency, my complete angle will change, and this angle here I represent by this subscript I, right, where this is the instantaneous angle, which in terms of omega is represented by this, and in terms of frequency omega is 2 pi f. This is how I represent, where fi is my instantaneous frequency. True, these are the notations we must be careful about. Now, since the complete angle changes, may I represent my angle as 2 pi fit? If there is little variation in this with respect to time, the change I'll represent by d by dt, right? Change in the angle with respect to time. If I want to see the small change in angle, how do I represent it? D by dt of my complete angle. When I do it, this removes the term t. When term t is removed from this expression, may I write my instantaneous frequency as 1 by 2 pi of d by dt of my angle. So from here I get a value which is my instantaneous frequency, right? That is, this frequency is proportional to rate of change of angle, true, d by dt of angle, right? And this is a constant term, 1 by 2 pi. Now fc is the unmodulated carrier and fm is the modulating frequency, that is frequency of my message signal. Then we may deduce that instantaneous frequency is equals to constant carrier frequency plus the deviation, and this deviation is represented by this, and here del fc, that is change in carrier with respect to time, which I may write it like fi equals to fc plus del fc into mt, right? Considering the amplitude of my message signal to be unity, I may expand it as mt as cos omega mt, right? My mt is usually my am cos omega mt. For my ease, I may consider this term to be unity and I may write it like this. So here this complete can be written as this from here, right? Now let's compare. Here del fc is the peak frequency deviation of the carrier, that is how much there is deviation from the central frequency, from the carrier frequency. And so I have 1 by 2 pi d by dt of my angle change is represented by this. From here I may deduce that rate of change of my angle will be, I may write it as 2 pi fc, this term will come here, and 2 pi del fc cos omega mt, right? I hope it's clear. Now if I want to see the if because of the frequency how much is the change in complete angle, what do I have to do? To remove the dt term, I have to do integration. If I want to remove that, I want to actually see what are the parameters on which my frequency and phase depends. Integrating it will help me achieve integration of omega c will give omega ct. Integration of this will give me 2 pi del fc cos omega mt. It will remove dt by angle, right? So this is the integration of my equation. So from here I may write my instantaneous phase angle to be omega ct plus I may remove few terms from here, and what do I get? Here omega m can be written as 2 pi fm. So this 2 pi gets cancelled. I get del fc by fm here, sine of omega mt, right? Hence, I may deduce the equation for my fm signal as, my fm signal might be represented as, here this represents my modulated signal. This will have the instantaneous frequency, instantaneous angle, and this can further be expanded as that my modulated wave expression for FM signal is Vc cos omega Ct plus del Fc by Fm sin omega mt, right? So because of the variation in frequency, what is the final expression for my modulated signal? This is represented here. So if I am asked about how may I represent my frequency modulated signal, I may represent it with this expression, right? If instead of V, if you are using ST terms, instead of V, if you are using A terms, and if you are representing your output signal or modulated signal by ST with different notations I am writing, you may write as AC cos of omega Ct plus del F frequency deviation upon Fm sin omega mt. So this is how you may represent your frequency modulated signal, right? You can see a term here. This is the factor by which is introduced because of the variation in frequency, right? And this part represents your message signal. Here the frequency del Fc by Fm is called as modulation index, and it is usually denoted by beta. So in case of frequency modulated wave, my modulation index is the ratio of my peak frequency deviation to the modulating frequency, which is my message frequency, right? So with a note, Fm is as implicit in the above equation for VST, is a non-linear process, that is, the principle of superposition does not apply. The FM signal for a message MT as band of signals is very complex, hence MT is usually considered as single tone modulating signal of the form, where MT message signal is represented like this, right? So the generation and next part will cover